Hello everybody, this is part 2 of chapter 1.3 and we're going to talk about linear combination in one-dimensional space or in R1. So what is a linear combination in one-dimensional space? This is just a scalar multiplication. We take our vector, for example v here, and multiply it by a number or weight c. So, and we often see this the scalar multiplication referred as a weight. Okay, so let's just try to experiment a little. So let's take a vector v, and it will be 2, 1, which means like 2 on the x-axis, 1 on the y-axis, and we try different scalar multiplication of this vector. For example, let's take a weight -2. So in this case, our c is equal -2, and let's see what kind of vector we get if we multiply our vector v by -2. We should get something which is twice longer and point in opposite direction, which that's what we have. But we also need to very carefully distribute -2 among the vector component, and we get actually coordinate of this vector, which is -4, -2. Wonderful, but you've done it probably, it's in the previous video. So let's do something a little bit more challenging. So let's take a point. The point which is on the same line as our vector. Let's say x coordinate 3 and y coordinate 1.5. And let's see what kind of linear combination of vector v will give us this point. Or in other words, what kind of weight of parameter c will give us this point. Okay, let's start with our vector and the basic definition. CV is equal u. You will see me using the definition a lot. I think it's a good habit to always start mathematical problem with a definition. Okay, so now let's use numerical values for our vector v and u. So our c, we don't know, we want to find it, but our vector v is 2, 1, and our vector u is 3, 1.5. So now it looks like we have a system of equations which we need to solve to find our weight c. Let's distribute the c in our vector. Again, is just multiplication of vector by number. I know the number here is a parameter c, but there is nothing wrong with that. So we will get two equations with one variable c, and that one is reasonably easy to solve. C is equal 1.5, give a true solution for both top and the bottom entry. So we are, actually that's the weight, that's what we're looking for. So we right now can write down our solution as a linear combination. Weight 1.5 times vector v is equal u. Or you can expand it in the numerical value if you prefer it this way. Okay, so this is when we know this point we're looking for is actually line on the line. But often we do not know. So what if we have a vector like u, for example, 6, 9, which we don't even know if it lines on the same line, how we can figure out if it can be written as a linear combination of our vector v? Again, we can start with our basic definition of the linear combination in one-dimensional space. Weight c times v is equal u. And we again try to solve the system of two equations to find the value for our weight c. And we just substitute again our v vector to 1 and our new u vectors. So again, we have two problems, and the u, even though notation is the same, this is a quite different u now. It's 6, 9 now. Okay, we can distribute the c and make the calculate basic matrix operation. And we have two equations which tell us two quite different things. The first tell us that c is equal 3, and the second is c is equal 9. So that's a problem. There is no weight C which satisfied both of this equation, which means that that's not the right equation. So the solution for this equation does not exist. In other words, our vector u, sorry about that, it's not a w, it should be u. So our vector u cannot be expressed as linear combination of vector v. That's probably because it does not lie on the line. So how do we know what lies on the line and why line is important? We can call all set of linear combination of our vector v or any other vector as a span. So basically our linear combination in one-dimensional space, but it's actually true in any dimensional space. We will see this example later, but in one dimension, span of a signal vector is just set of all its linear combination. Every single weight, which you can imagine, which is infinite number, will give us a new linear combination vector. And all of them will form the set, which called span. So what is a span of vector v? Clearly, to be a linear combination of vector v, we should be on the line included by v. So what kind of line is this? I mean, it's a convenient one. It passes through the origin. So all we need to do is just find the slope, which will be a half. So basically, equation of our line is y is equal 0.5x. Or in other words, we can say the span of our vector v is equal 0.5x. Okay, and that's all about the linear combination in one dimension. The next part will be a linear combination in R2.